TiDB, as I mentioned, it does enormous scale. It is MySQL compatible. It's adopted by some major financial institutions in the United States right now. It has passed most of the security compliance certifications that you expect to be out there, and most importantly, in my opinion, it's 100% open source. We've got north of $500 million in funding from some of the most notable VCs out there, and over 3,000 customers across 25 countries, over 500 employees stretching 9 different countries. So we've got a pretty good footing. We've been doing this for 10 years now. Part of the reason why you haven't heard about it that much in North America is because North America is actually the last expansion market that TiDB expanded into. But we're gaining foothold, we're gaining traction in North America very, very, very quickly. You know, I've been to probably about 5 conferences this year, just because this kind of thing is sort of my thing and what I do. And I can tell you that walking the floor at every single one of those conferences, from GCP Next to Kubernetes conferences to the AWS reInvent, one thing stood out above all else, and that is that almost every single booth out there was AI something. If there was one major learning out of all of this, it's that it's AI everywhere right now. I'm going to go so far, and I've actually started really pushing this into our own company, of saying that if you are not actively right now studying about AI, if you don't have a paid ChatGPT account yourself, no offense, but you're probably actively working yourself out of a job, like at the moment, if you are not actually using some form of AI deliberately right now, every single day. And I actually do not think that that's an overstatement, and I don't think that it's alarmist. I think it's just a fact of reality of where we are today. And unfortunately, time is going to tell if I'm right, and if I am. I hope that a large enough mass of people actually get themselves tooled up so that we can all contribute. How many people are familiar with Dan Roberts? Okay, Dan is one of the chief researchers at OpenAI. I'm going to actually ask you, hopefully I don't get any copyright infringements on this. He gave this talk, and Sequoia posted it on LinkedIn, and I actually loved it. I want to play just a short snippet, about 20 seconds of it, because it illustrates what I'm going to talk about today.
Coming back to this plot, how do we get there? Well, now let's focus on the left plot. The performance of the model improves the more we train it. And the sort of training we do is RL, or reinforcement learning. And so the main thing that I want to communicate in this talk is that we want to scale that up. A year ago, we put out GPT-4o. There was compute used, and it was all pre-training compute. And as you can imagine, then we started doing this thing that led to test time compute. So we added some reinforcement learning compute, RL compute for O1. I should say this is all a cartoon, but directionally it's correct. O3 maybe had a little bit more RL compute. At some point in the future, maybe we'll have a lot of RL compute, and then at some far point in the future, maybe we'll have just be totally dominated and crushed by RL compute. And this is I think is kind of a contrarian point of view. This is where we're going. And we mean it to emphasize sort of the contrarian nature of this. This is, some of you who followed AI research, this is a slide that Jan LeCun made some number of years ago, I guess 2019, based on copyright that I borrowed this from, obviously. This is a complicated slide that's maybe hard to follow. Luckily, we have models that can summarize things for us. The point is that pre-training is like this big cake, and reinforcement learning is supposed to be like this little cherry on top. And that's basically what this plot was. The color scheme actually was accidental, but I think it actually works quite well. And this is where we're going. We want to totally invert the meme here. We have maybe the same size cake, and we just want to crush it with a giant reinforcement learning cherry. Okay.
So that's kind of where I want to stop at, is right on that meme right there. What you have is this little tiny cake. Does everybody get what the little cake is? This is significant. So LLMs, large learning models, such as ChatGPT, their elementary training is the body of the internet. That's the cake. The cake is the body of the internet. And what he's saying is that the reinforcement learning that they're going to be doing on top of that to refine the training is going to be bigger than the body of the internet. So big that it essentially is crushing in weight of how big that data set is going to be. We also get that it's a data set. Follow me on this? Hopefully now you're starting to see where I'm going with this, right? This is a problem like we've never seen before. And it's going to be a problem that's going to show up in your company. Or your company is going to be one of those companies not doing AI, and who knows how many of those are going to be around, basically. So, how many have heard this term Gen AI? Okay, almost everybody in the room. So I'm going to go through a couple of slides here that are going to be a little bit of elementary vocabulary. And really, I want to run through this fairly quickly just because I want to make sure everybody is level set so we're talking the same language. Gen AI, basically, in short form, is an intelligent program that creates something. It generates something. It could be an image, it could be music, it could be text, it could be a response to a prompt, something, but it creates something. So how about an LLM, or also known as an LRM, a large reasoning model? These are things like ChatGPT, Claude, there's several others out there today. What they do is they are AI agents that are, AIs that are trained on a specific set of data, and then they build something off of that training in response to a prompt. But it's all dependent upon a prompt. So you give it a prompt, it gives you an answer based upon the training that it has been put through. It needs data, but that data is old data. It's historical data. The body of the internet today, if we're talking about immediacy, is pretty much already stale because, time launches forward and things get stale fast, really fast. An LLM is part of a Gen AI stack. It's part of the Gen AI architecture. It's basically the foundational level at the very bottom. On top of that, we have a layer that has become very popular today with companies out there who are building their own that is called RAG. Everybody familiar with or have heard the term RAG? Yeah. Okay, so it's retrieval augmented generation. This is basically retrieval plus generation. What this means is that you have a storage of data someplace. Maybe it's industry data, maybe it's your company's specific, industry secrets data, whatever it is. Maybe it's your customer list, your CRM. Maybe it's their ordering, history or their support tickets, whatever it is. You have an AI that is going to go search that data, and it's going to use that data to put together a much better prompt to send to the LLM. You can think of that as newer data, fresher data than what's in the LLM. A lot of times, most of the time, these are either going to come out of a graph database or they're going to come out of a vector database, or both. Most of the time it's going to be both, okay? And it doesn't have to be a graph database, doesn't have to be a vector database, but it has to have those capabilities. The database has to be capable of producing graph results, it has to be capable of producing vector results. Graph is usually used for structured data to identify or find explicit relationships. The vector data is usually used to find things that are similar, most similar. And then, if you put all this together in a specific form for a specific purpose, we call this an app. We use this like a RAG app. We have one that is called TiDB.ai, which I'll talk about a little bit later. It's sort of a reference model RAG app that we've built that actually searches all of our documentation and a lot of our backend knowledge to produce answers for the open source community, for our support teams, for our Discord channel, questions on how do you work TiDB, how do you install it, how do you scale it, things like that. When you take that and you wrap it all in something that has this characteristic of agency, and what that means is that it has a certain amount of autonomy to actually complete a certain task, you have an agentic AI app. Everybody follow this? Yeah. All right. So I want to talk about this idea of context memory, because this whole thing now is about context memory. Has everybody heard of this term memory in AI? We hear it thrown out there a lot, but what is it? Well, the short answer is it's data. It is data, that's what it is. But it's different kinds of data at each of those different layers of the architecture. At the base layer, the LLM, there is memory, there's context memory. This will be memory about your session. This will be memory about, not only the questions you asked, but the spelling that you used, the voice tone that you used. Do you have biases in the way that you ask questions? All of these things can, not only does it store what you asked and what it said, but it makes inferences about you and about what you're looking at, what you're researching. Those inferences also get stored as well. At the RAG layer, this is going to be persistent information, structured embeddings, documents, and again, if there are inferences that are made at the RAG layer, it may store those also. This is more up to you because you're probably going to be the team who's building the RAG app. And then at the agent layer, this is where it stores information that has driven decisions. Okay, so if you have a more complex RAG setup where you're doing now agent-to-agent communication, where you have agents helping each other to do things, think supply chain, fully automated supply chain that is completely run by AI agents. Okay, those agents themselves may have memory, and they're persisting runtime management. So they're persisting maybe IP addresses and MAC addresses plus ordering characteristics, routing and shipping schedules, stuff like that. And this stuff is going to be updated fairly frequently. But it means something at each layer is what is important here. You've got memory at each layer, but at each layer that data is doing something a little bit different. Why is this important? The reason that it's important, actually before I go through that, I came up with this little human analogy that I want to throw out there to everybody. One of the things that I learned right away is that one of the easiest ways to gain a good understanding of what's going on in this architecture is to think about it in terms of human reasoning, human thinking, human learning. So we might think about elementary school. We all remember at least some of our elementary school years, right? We learned quite a bit. It was good. And then we got to university. How many people in the university, once they got there, realized that at least 50% of what their parents and their teachers taught them in elementary school was completely false? Right? It happens. Okay, either the data was stale, or it was flat out wrong, or it was based off of inferences that were flat out wrong. And so you did some relearning, and you have fresher data. But the thing about university learning is, and if there's anybody in university right now, I'm sorry, I'm just going to give you the raw truth. It's a little idealistic. What you learn is the way that things work in a perfect society, and the way that things are always supposed to work, and it's a little bit, Pollyanna-ish. And when you get out into the professional world, you realize that the world is messy. It's not like the ideal state that you learned about when you took your Accounting 101 course. You end up with stuff that doesn't fit into nice T accounts really, really well, really easily. You find out that not everybody documents their code absolutely perfectly. You find out lots of different things, right? That the world doesn't follow these nice, tidy, orderly little sets of rules that work really, really well because you learned about them in university. So what you gain there is professional knowledge, expertise, experience. Each one of these leading up to the professional experience is generally a finite amount of data. It had a start point, it had a stop point, but think about your professional experience. How many are more than 5 years into their career? I'm going to stop there out of respect for most people in the room. At what point did you stop learning in your career development? You don't, right? You don't. It goes on infinitely. So you're capable of ingesting and storing an infinite amount of data as you mature. Okay, if we flip this into how does this apply to agentic AI, your LLM memory is the body of the internet. Your RAG memory is your RAG data. It's your professional data. It's the data about your industry. It's the data about maybe it's regulations, stuff like that. It's finite. But this over here is the data about your ongoing business. That's context. That's historical context. And it could grow infinitely. Now the question is, okay, well, why don't we archive some of this? Why does it have to grow infinitely if we keep this in human context? and I were to tell you, okay, your memory has a limit, so you're gonna have to choose which of the memories in your mind. And bear in mind that you are the person you are today because of every single one of your experiences that you carry with you. So tell me which of the experiences and memories in your head right now that you're willing to delete permanently. Your company is going to be faced with the exact same question. You follow me? Not only is this going to become the single most important piece of data, the single most important data footprint that they have in their business, in their company, it's potentially going to be their company differentiation, their competitive differentiation. It may even ultimately become the identity of the company. It's going to be that important to them. So that context database over there on the far right has the capability of becoming the largest data footprint in the entire company, bigger than any system of record or data warehouse that exists today in the company. Everybody follow me on this? Okay. Now, when you heard a friend from ChatGPT talking about how this happened down at the LLM layer, he was just talking about the exact same thing happening with the initial training data and then the reinforcement context that they laid on top of it to say, well, not this but that, not this but that, refine this to that. The reinforcement learning that made it get better and smarter over time. Well, you're going to have the exact same things in your RAG apps and in your agentic AI applications, but they're going to be behind your firewall or your AWS VPC, and you're going to maintain them. And you're going to maintain a database that is the size and a scale that you've never maintained before. Make sense? Okay. We believe that there's actually only one database out there today that has the capability of servicing all 4 of these workloads in one single database. And we believe that that's TiDB. There's a lot of databases going on down here at the LLM layer. I actually can say that some of them do run on TiDB, but we don't, and you won't have control over those. But just know that those who know are using TiDB. What I'd like you to do now is just take this image, burn it in your mind, and think of it as a cell. Okay? It is an architecture cell, right? It's a very tiny architecture that is going to be used to build out massive multiple systems. If you think again about the human body has billions and billions of cells in it. This architecture is going to be repeated over and over and over and over again as these agentic workloads start to multiply. Not from company to company to company, but from line of business to line of business to line of business. From workload to workload to workload to workload. Cells build solutions. You are a walking, talking, eating, living, breathing solution of a group of cells that built something really, really complex and really cool. Same exact thing is going to happen as this AI technology evolves. It looks like this today. These cells build out orchestrations that actually take user input, do processing, go through a retrieval phase, go through contextualization, go through tokenization. They do data processing on the things that they tokenize. And as they're doing all of this, they today require an entire array of different types of databases. From relational databases, vector databases, graph databases, doc stores, metadata stores. Every single one of these types of data stores gets utilized and gets hit just to get a prompt, just to get the question right that gets sent down to the LLM. You follow me on this? Okay. Sprawl has always been an operational challenge, and we've heard it talked about for decades. That so many different databases doing so many different things. We've got sprawl all over the place, and we have this massive operational overhead because now we have to have 15 different skill sets because we've got 15 different. The issue now is that we have a new kind of problem. We have sprawl plus scale. We've never had that combination. We've never had the combination of sprawl combined with scale prolifically everywhere. That's the problem now, and that's the problem that we're solving. We think it can be done with a single database. We think that there is a database out there that has vector capabilities, that has graph capabilities, that has relational capabilities, that can store JSON, and that could actually be a very, very, very viable way to simplify this entire thing. Option A or option B? So what makes TiDB a good fit for this workload? Again, pretty much everything that I just went over. You can do vector search with it. If you do graph traversals, you can do keyword search, you can store unstructured data, you can use it for analytics, and you can store SQL. It is a distributed SQL database, which means that it is a relational database at heart. It has high availability built into it through the Raft protocol. I don't have any slides on the architecture, but I will run through a couple of pieces, actually because of our friends here from Altinity. But you also have the ability from the row store to automatically copy data to our columnar store. And it copies the data to the columnar store in real time as part of its ACID compliant strong consistency. That column store that it's copying to is actually a highly, highly optimized version of ClickHouse that is optimized for TiDB. So this is sort of our tie-in to ClickHouse as well, and kind of why we're all here together, is that we're all ClickHouse family friends. So let's talk about a couple of examples of this architecture being used inside of some AI use cases. I talked about TiDB.ai. So the first thing to note is that it's actually fairly simple in almost any graph data, any relational database, to implement a fairly simple graph traversal set of tables. Really what you need is to be able to, a table to be able to identify the entities, the relationships, and then you need to be able to break it into chunks and do vector searches on it. If you can do that much, you can do the graph traversal that's necessary for an agentic use case to actually pull RAG data, do the type of tokenization that it needs to do, create a prompt that is going to actually be performant and help you get a more accurate answer. If we walk down the steps real quick, and these are the steps that actually happen inside of TiDB.ai, we start with determining intent, which means that we take your prompt, call a query, go through decomposition from it, do graph traversal on it to figure out what on the back end we already have in terms of documents, in terms of tickets, who's had this problem before, and so forth. We do the graph traversal to compare it through vector search to any type of inference that may have actually solved this in the past. We do query optimization off of that to create a better prompt, and then we actually do a vector search to actually narrow it down to the top 100 matches, which are going to give us the highest probability of having a good prompt. And then from that, we actually get the prompt that we want, submit it to the LLM, and then give you back the answer and the response. And we actually iterate through this process a few times. We use an autoflow, and I'll show you, it's open source, so you can actually go look at it yourself. And it's actually pretty cool because you can see it branching, and you can see each time that it loops and it branches, and you can see each inference that it's making at each point. And what you actually have the ability to do is pause it at an inference and adjust the information that you're giving it. So if it's going down a path that is completely out in left field, you can stop it at that point and go, no, I didn't mean this, I meant that. That architecture implemented in use cases, again, you can go out to TiDB.ai today and you can just start asking questions about our database and it's going to start giving you answers. It also has an API, so you can access it through an API. That API is built into our Discord channel. So anybody in our Discord channel, in our open source community who has a question or a problem can actually just ask the question to @TiDB.ai and they'll get an answer. It'll respond to them in Discord. We use it inside of our own support organization. So our own support engineers actually use this as well. What it's actually become is a faster way to search our backlog and all of our solved tickets than any other way that we have today. We have built something like this into our own cloud DBaaS product as well. So if you go out to TiDB Cloud and you launch a serverless cluster, you can get a SQL editor, and inside of that SQL editor, if you do a command I, if you know the general idea, the natural language description of your tables. So for instance, let's say that you synced down all of the metadata about all of the GitHub repos out there, and we actually do this. We have another reference application out there called OSS Insights, where we sync all of the metadata from GitHub. So if you were to say, what is the most commonly used, or what are the 5 most commonly used programming languages, and rank them by 1 by popularity and then 2 by project stars, something like that. You would be able to say that in natural language into this prompt, and it would give you all of the SQL to go get that out of all of that synced GitHub data. And it's using the exact same graph traversal and lookup that I went through before, and that all of the rest of our TiDB.ai features use. Now, I'm actually not trying to sell TiDB.ai. Hopefully I'll make that clear. What I'm trying to point out is that that's a reference of what is possible to build. It's just one reference application. You guys are going to build something that is completely dedicated and focused on your business, and it's going to be really cool, but it's going to generate a full metric boat ton of data. That's an actual scientific measure. Didn't know that. The last one is that we actually have it built into the database. We have index advisors that you can download and just let it scan your database, and it's going to give you tuning advice. It's going to tell you, hey, you got a lot of traffic hitting this particular table. These indexes will actually help performance. Real world use case. Anybody here know who Diffie.ai is? Yes. So they are one of the companies that are now doing agent as a service. So you saw the agent architecture slide. The architecture for agents is becoming so common now that there are companies out there that are offering agent as a service. They're using TiDB on the back end. When I said, the companies that know. And for them, 400,000 databases. That's what their footprint was. And they replaced it with TiDB. I mean, the numbers are speaking for themselves. When you talk about sprawl plus scale, it becomes really, really, really obvious that it's a problem that people need to solve. And I can't think of another database that is like in the chute right now, ready to take it. Pushing the wrong button. Okay. Final thoughts just to wrap all of this up, and I think I may need back some of our time for the next speaker. Going from this to this can be done. It can be done with a database that's out there today, and if you want to know more about how it works, find me after the show, and I'm happy to run through it with you. And if you want to go out and try it right now, this code will get you to TiDB Cloud, where you can sign up for a free TiDB Cloud account. You get a free serverless cluster and start using that today. The link to TiDB.ai is down there as well. If you want to check out our Autoflow, it's on GitHub. And then we actually have stood up a labs for TiDB.io as well, and you can get information about the API from that. All right? And while our next speaker sets up, I can start taking some Q&A myself. Yeah?
This may be a basic question, but how do you, quick presentation model, how do you ensure low latency and high throughput?
So,
Perennial problem with it.
yeah, no, it's a good question. Yeah. Did they ever set you up to how connected?
That helps you differentiate yourself from other.
Yeah. Yeah, let me disconnect from this real quick and let them get set up. So, TiDB uses an architecture that separates compute and storage. The way that distributed architectures differ from a traditional architecture is that in a traditional monolithic architecture, you went over it when you talked about ClickHouse. Having your compute as close to your data as you can works until you outgrow that box, and then it doesn't work anymore. And what happens is you end up having to stretch it across multiple machines. That's what distributed SQL does as well. We basically shard the data across multiple servers, but we're separating compute and storage as well. So the compute layer, if you think about, there's some architectures out there like Aurora. So Aurora has a distributed storage layer, and they separate compute from storage. But one of the characteristics that they have is that you can scale reads out by just adding more read replicas, but you still can only have one writer. So even though you've got distributed storage and you've separated compute and storage, you're still bottlenecked on the write window, right? When we do it, all of our nodes, our compute nodes, are open for read-write. So this allows us to scale out write throughput and distribute it evenly. Plus, you can do it for read input as well. There is a small amount of latency compared to a single server monolithic architecture. So if you think about the graph, the entry point latency for a distributed SQL system is going to be marginally higher than what you're going to see in a monolithic database, like a single server MySQL database. However, as your data footprint grows, like what we're talking about here, that single server's latency is going to hockey stick quickly and spike hard. The TiDB latency curve is going to start out slightly higher and stay flat. You follow me? And when we're talking about incremental differences in latency, we're talking about going from 1 to 5 milliseconds of latency to 5 to 12 milliseconds of latency. So it's not a massive amount. You might be able to say, well, yeah, if you go from 5 to 10, that's 100% increase, but it's still 10 milliseconds. Yeah. Yeah.
So for application, you do vector search, but you are not like Pinecone, you are not vector database. So you recalculate the embeddings every time when you search, when you do search.
So our vector search is a vector data type and vector indexes. We're not a complete vector database. So you can actually, we will use the vector indexes in an SQL query that is submitted with a vector predicate.
You store your vector indexes.
Yeah. I have to say that's pretty much the limit of my knowledge on vector database.
Yeah, you're not you're not just a database in that sense. You're not,
Well,
you're not providing the data.
Correct.
Yeah, that's what we.
Well, we are a database,
Yeah, but
but we're providing the exact same capabilities
Right.
that all of the rest of the 15 databases that are sitting under most agentic AIs are providing. Do we provide it at the level that each one of those provides? Probably not, but we provide enough capabilities that you actually could consolidate into one. Should we use this one? You got, so
how did you, it's good.
we've got this one, or we've got the handheld, or if you got both, use both. You're gonna go acapella?
Hello?
You got a jack of the lapels, so it won't work.
They not